Okay, so this sounds like a big deal, and it kind of is. It's called the Fundamental Theorem of Calculus, Part 1. We'll get to Part 2 tomorrow. Okay, so first thing I want to point out is little f is a different function than capital F. They're not the same function. Capital F is a different function than little f. So capital F is an interesting function. This is a number. The a is a number. So maybe it's 3. So if you plug 7 into capital F, that means find the area from 3 to 7 underneath little f. So you would need to know what little f was to figure that out. But somewhere there's a graph of little f, and capital F is the area under that function. So if you plug 10 into capital F, you would find the area from maybe 3 to 10, et cetera, et cetera. So sometimes I call the capital F function the area up to function. It tells you how far to find the area. Like if you plug 7 into capital F, you find the area up to 7. Okay, so capital F and little f are different functions. Excuse me. And what we're saying here is that this capital F function, the fundamental theorem tells you that this capital F function has a derivative. So we're going to learn how to take the derivative of this mess, how to take the derivative of this capital F. So it has a derivative, and what the derivative is so I'm trying to figure out capital F prime. And so to figure out capital F prime, I can just take the derivative of what the capital F is, right? Sitting there is the capital F, and I'm trying to figure out its derivative, so I just slapped a derivative sign in front of it. And that's also called capital F prime, because this is capital F, so the derivative of it is capital F prime. Okay, so the fundamental theorem says that this brand new function called capital F, which is a weird function, has a derivative, and the derivative of it is, so I'm about to tell you the answer to what this derivative is. The derivative of it is little f. Now, I don't expect you to believe me that that's true, but here's what that says. We spent chapters 2 through 4 working on derivatives, right? We said, okay, we got to do all these derivatives, take the slope of things. And then we switched gears in chapter 5, and we suddenly started doing area. So we did slopes for a long time, and then we did area for a chapter. And it seemed like those were unrelated, right? But what this says is that area and slope cross each other out. They're inverse functions, like plus and minus, undo each other. Or times and divide undo each other. So apparently area and slope undo each other, and you're back where you started, sort of. That's why it's the fundamental theorem of calculus, because it takes derivatives and connects them with integrals and shows how they relate to each other. Okay, so let's try a problem. Let's say that capital F of x is the area from 3 to x underneath t squared dt. And we're going to find capital F prime. So we have this weird function that finds the area from 3 to x underneath t squared. And we're trying to find the derivative of it. Okay, so if we're trying to find the derivative of capital F, we need to take the derivative of capital F. And what do you get when you take the derivative of this? X squared. Okay, now people always wonder, okay, I see where you got the squared, because those cross out, see what I'm saying? But why did the t change to x? So here's at least a decent answer about why that's true. Capital F is a function that inputs x. The input variable is x, right? So the derivative of it needs to input x as well. The only reason these are different is because if that was an x, we might accidentally plug our number into both of those locations. So we need them to be different, so that when we plug a number into this, we just plug it there. But then, since the input for this is x, then the derivative's input needs to be x as well. That's why it's x squared instead of t squared. But the big deal is that when you take a derivative of a strange integral function like this, you just get back to the function that you started with on the inside. So mechanically, it's not hard. You'll just watch those cross each other out. You'll write down the answer. Because I told you that that's what's supposed to happen here, right? Now, knowing why that's true, we're not tackling that today. You're just supposed to believe me that this is true, which is different than what I normally do. Normally, I start with why and then get to what's true. But for today, I'm telling you, this is true. When you do this derivative, you get x squared. Is everybody doing okay? Okay, things get a little bit tougher than that, but not crazy tough. Or u, whatever u, cursive u or mu, sure. Yes.
Does it matter?
It's just a variable. So no, it doesn't matter. It doesn't matter what this letter is called.
Okay.
Yes. Okay, so the first thing that bothers people about this problem is little f here corresponds to capital F over there, right? People don't like that. Over here, I was calling the area function capital F. Over here, I'm calling the area function little f. That doesn't matter. It doesn't matter what the area function is called. I just need a name for it. So in that theorem, this is little f, right? And that's capital F. But since I don't have a little f here, I could call that little f, and it doesn't matter. Okay, the next thing that bothers people, oh, so what's the next thing that's different about this problem as opposed to this problem? The 5x, that's not just an x. In this problem, that's not just an x. And we don't know how to do the derivative when that's not just an x. The theorem that we have just tells us how to do it if there's an x there. So we need to play around a little bit so that we can figure out the derivative of this. Okay, so what I'm going to do is I'm going to make a new function called h of x. And it's going to be the integral from 4 to x underneath this. So why do we like this function better? Because we know how to take the derivative of this function, because there's just an x there. But we don't like this function because it's not actually the one we're trying to take the derivative of. So we're making an exchange there. Okay, now I'm going to have g of x be this function, 5x. Okay, so if I plug 5 into h, then I would find the area from 4 to 5, right? If I plug 7 into h, then I would find the area from 4 to 7. So if I plug 5x into h, then that would be the area from 4 to 5x. Okay, so what's the fancy name for this kind of a thing? When you take the derivative of this kind of a thing, you need to use chain rule. Good. And that means that this is called a composition. Okay, so what I did was I noticed that if this was h of x and if this was g of x, then the thing I'm trying to take the derivative of is a composition. It's this plugged into that. And so thus, when I take this derivative, I'm going to need to use the chain rule. Okay, so how does the chain rule work? How do you take the derivative of something like that? Well, there's the outside function and there's the inside function, right? So the way you start out, you take the derivative of the outside function, and you plug the regular inside into it, and then you multiply by the derivative of the inside. Okay, so the outside function is h of x. What's the derivative of this h of x? Radical 1 plus blank squared over, yeah, keep going, Rebecca, you're doing good. Over blank squared, awesome. is everybody okay with this being the derivative of that? That was the fundamental theorem, the new thing for today, right? Is everybody all right? Okay, so there's the derivative of the outside function. Now I need to plug the inside function into it. So what do I plug into this? 5x is the inside function, awesome. And then to finish out the chain rule, I need to multiply by the derivative of the inside, which is 5. Everybody okay? So that is f prime. Okay, so we've got this new fact here, and I practiced it once. And then I threw in the new fact with chain rule, which is something pretty hard from the past. So that's why this problem was pretty tough, because I only practiced the new fact one time, and then I linked it with something hard from the past. So is everybody okay? Okay. So George, basically what we learned was, in this mess, was that the derivative and the area functions cross each other out.
Okay.
That's an oversimplification, but that's in 30 seconds or 10 seconds what we learned there.
Okay.
Good. Okay. See where we are here. Oh, yes. Okay, for example 3, we are going to construct a function f of x so that f prime of x is 3. So I'm going to give several answers. Or actually, you could probably give me several answers, or at least one answer. What's a function whose derivative is 3? 3x, right? Okay, good. So easiest answer is f of x equals 3x. Okay, easy enough. What's another possibility? Yeah, Zach? 3x plus 7, or 3x plus anything, right? Because if you take the derivative of 3x, you get 3, and if you take the derivative of 7, you get 0. So then the derivative is 3, right? And Zach was pointing out that that could be anything, right? It could be 3x plus 1,000. Everybody good? Okay, those are the ones that everybody thinks of, but here is the strange answer that uses today's fact. So I want us now to use this. Use this to answer this question. So what that would be is f of x equals the area from 4 to x underneath 3. Because if you take the derivative of this, the integral sign goes away and you're left with just 3, right? And remember, that can be anything. The a over there is just a number. So it could be 7 to x underneath 3, or 12 to x underneath 3. Oh, isn't it interesting that this could be anything, and this could be anything? There is a connection. We're not ready for it yet, but there is a connection. Is everybody okay with this crazy answer? I mean, if I ask you this question, clearly you're going to give one of these answers. Probably. But this is a possible answer, right? Okay, we're going to construct another function now. So we're going to construct a function so that the derivative of our function is this. And also, when you plug 8 into the function, you get 0 out. Okay, so on the last question, when I wanted my derivative to be 3, it was easy to come up with a formula whose derivative was 3, right? Because the derivative of 3x is 3. Is it easy to come up with a formula whose derivative is this? No, that's hard. It's backwards product rule or some craziness like that, right? So I don't know how to find a function whose derivative is this. So in example 3, answer 1 and answer 2 were easy to find. But in this problem, answer 1 and answer 2 are not easy to find. So what is easy to do? Just slap an integral sign on this thing and you've got the answer, right? So if I want to find a function whose derivative is this, I can just do this. Yes.
Where's the 12 from?
So in the theorem, it says a. It can be any number.
Okay.
So over there, I put a 4 there, and this time I put a 12. It doesn't matter. It does not matter what it is. It doesn't affect the derivative. So I keep changing it to emphasize that it doesn't matter. Good. So what's the derivative of this function? E to the x cosine of x, right? So we've got this satisfied. Now we don't have this satisfied yet, right? What happens if I plug 8 into this function? Well, then I have to figure out the area from 12 to 8. I guess we'd have to do math 9 for that, right? Use our calculators and plug in math 9, area 12 to 8 of this. I don't think it's 0. I'd be very surprised if I picked the perfect number here that would make it be 0. Kasha's going to check for me. Why do I want it to be 0? Because this is supposed to spit out 0 when I plug in 8, right? the area from here to here is supposed to be 0. How could an area be 0? If some of it was above the x-axis and some of it was below, right? They could cancel each other out. Is it 0? Okay, good. So I'm not done yet. So how could I make this function spit out 0 when I put in 8? What if I put an 8 here? I said this could be any number. Well, if it can be anything, why don't I make it 8? And then if I put 8 there, I get 0. Carter's annoyed with himself. He's like, oh, I should have thought of that. It's okay. Is everybody okay? Yes. Yes, so this thing down here can be any number, and then the derivative is e to the x cosine of x. So when I made it a 12, the derivative was this. But if I made it an 8, the derivative would be that. So now I've got my function, and if I plug an 8 into this function, that puts an 8 there, and the area from 8 to 8 is obviously 0. Good. Everybody okay? All right, we need to talk about, we're going to switch gears now and go back to particle on a number line moving, the classic calculus problem. So the question is, how can you tell if a particle is moving towards the origin? The question on the table is, how can you tell if a particle is moving towards the origin? Okay, so this is the classic problem where we've got our number line, and here's the 0 mark, and the negatives are back here, and the positives are up here, right? Okay, so if you're over here, is your position positive or negative? There's the 0. Position's positive, right? And if you're back here, position is negative. Okay, so let's go back to here. Your position is positive. If your position is positive and your velocity is negative, then you're moving towards the origin, right? Towards the 0. So position positive, velocity negative. So s of t positive and v of t negative, right? On the other hand, let's say your velocity was negative. Sorry, let's say your position was negative, right? So you're back here. In order to be going towards the origin, what would your velocity need to be? Positive. You need to be going this direction. So s of t positive and v of t negative, or s of t negative and v of t positive. And you could summarize all this by saying s of t and v of t have different signs, right? On the other hand, to be moving away from the origin, s of t and v of t need to have the same sign. Okay, we're going to look at a graph for example 5. It starts out as a straight line, and it goes from 0, 0 to 4, 4. Then later it ends up going through 5, 2, but don't connect it yet. And then it ends up going through 6, 0, but don't connect it yet. And then it ends up going through 7, negative 2. And then it connects like this. In the end, it goes through 9, 0. Okay, so this is a picture of f of x. And then I'm going to give you further information that the position function is the area under this f of x. So this is called capital F in our fundamental theorem, right? But in this problem, capital F happens to be the position function. Okay, so for part A, the question is, what is the position at time t equals 3? Okay, so to figure out the position at time t equals 3, we have to plug 3 into the position function, right? So we need to plug 3 into this craziness. So we're going to plug 3 there. And what does this mean? All this notation here, it means find the area under that curve from 0 to 3, right? So all I have to do is come over here to 0 to 3 and find the area of that triangle. So that's 1/2 times the base of that triangle is 3. The height of that triangle is 3. So it's just 1/2 times 3 times 3. So that comes out to 4.5. And I didn't tell you this, but let's say we're in meters. So that means after 3 seconds, the particle is 4.5 to the right of the origin. So here's the origin. And 3 seconds have gone by, and it's here, 4.5 away. Okay? Part B is, what is the velocity of the particle. At t equal 5. So I have the position function. How do I find the velocity function? Take the derivative of the position, right? So velocity is the derivative of position, which is the derivative of this mass. Here's the position function, right? So I'm just taking the derivative of that position function. And what happens when you take the derivative of the position? So I don't know what's happening, but just in summary, what you missed was that that crosses out that, basically. Oversimplified, but that's what happens. Everybody okay? Okay, so if I want to know the velocity after 5 seconds, that means I just need to find f of 5. And what is f of 5? It's 2, right? The graph says that when you put in 5, it spits out 2. So I didn't tell you it was seconds, but let's say it's meters per second. Okay. At t equals 5 is the particle moving away from or towards the origin. At t equals 5 is the particle moving away from or towards the origin. Well, to figure that out, I need to know both S and V, right? Okay, so I already figured out that V of 5 was 2, which is positive. Did everybody understand why it was 2? Are you positive that you understand? So now we need to figure out S of 5, right? How do you find S of 5? Area from 0 to 5, right? If I figure out the area from 0 to 5, is that going to be positive or negative? It's going to be positive because the graph's above the x-axis, right? How could area ever come out negative? If the area from 7 to 9 would be negative, right? Okay, so, but anyway, whatever this number is, it's going to be positive. So since V of 5 is positive and S of 5 is also positive, that means that it's moving away from the origin. In other words, here's the origin. The position is positive, and it's going that way. So it's moving away from the origin. Okay, one more part, and then we're finished for today. is the acceleration at t equals 5. Positive or negative. So how do I find acceleration? Derivative of velocity, right? But what's another name for v in this problem? Another name for a is the second derivative of s, yes. What's another name for v in this problem? F of x, right? We said that the derivative of this, which was v, is f, right? So if I want to know v prime, I really want to know f prime. How can I tell what f prime is? Just look at the graph of f, right? And at 5, what is f prime? Positive or negative? Negative, because the graph is going down. Everybody good? Have a good one.